prime, I want to make that equal to lambda over 2. If I do that, then the rays A and B will be phase shifted by lambda over 2, and they will cancel each other. So if all I have to do is put a material of thickness D given by lambda over 4 times n prime. That's my answer. Okay, relatively easy, simple to think about. Now, I made some very simplifying assumptions here. First, I've assumed that the phase shift that occurs due to this reflection, this process here, is the same as the phase shift that occurs due to this process. Okay, that may not be true. It's a reasonable assumption. They may not be true because the reflection here happens from 1 to n prime, whereas the reflection here happens from n prime to n, right? So there are different situations. So it may not be the same. The second assumption I made is the fact that I've ignored the reflection at this interface in that direction, right? Obviously, I'm going to have some light bouncing back in. We will come back to that point later on. So keep that also in mind. And the other more fundamental assumptions we have made is that, okay, we're only considering one wavelength. We know for all cases, this is never true, right? This is only theoretically true. For human vision, of course, we are interested in all the wavelengths in the visible band. In the case of solar cells, of course, we are interested in all the bands, all the wavelengths that can be absorbed by the solar cell within the band gap of the solar cell, which we, by the way, will talk about on Tuesday. So keep those assumptions in mind. And there are a few other assumptions we'll come to, but those are the key things you can think about now. So again, just to summarize, rays A and B are out of phase by pi or lambda over 2, and then destructively interfere that prevents the reflection from happening. Now, you can surmise, as I mentioned before, that this depends on wavelength. So if I plot the reflection, which is in this axis, versus the wavelength, I can see that it changes with the wavelength, right? It's not flat. And that's because the refractive index n and n prime depend on lambda. Okay, they're not flat with lambda. So these are a few examples. The interesting example, let's start with the green curve, is that this is silicon under glass with optimal anti-reflection coating. Refractive index n is 2.3. The index of silicon is about 3.4 or 3.5, as I was saying before. So you can see that the reflectivity here goes to 0, but it only happens at one wavelength, in this case, 0.6 microns in the green, red, or yellow, red wavelength. As I go away from these wavelengths, the reflectivity starts going up, right? So this is something we, of course, have to be aware of and be careful about when we do the design. Now, if you don't have an optimal coating, you just put silicon under glass, you get much higher reflectivity, right? Much higher up here, but still better than not having anything at all, because the refractive index of glass is 1.5, is between the air, which is 1, and silicon, which is about 3.4, 3.5. So glass does something, not as good as a good optimal anti-reflection coating, but it's much better than just bare silicon, where the reflectivity is very high, right? Over 30% or something like that. Now, this is bad, right? This means that if I take a silicon solar cell, which is, of course, the most common solar cell, and do nothing to it, I'm going to simply lose, I don't know, greater than 30% of the power simply bouncing off the surface, which is a terrible waste of energy. So obviously, it's a problem we need to solve. And importantly, of course, we have to solve this in a cost-effective manner. So that's another thing we'll talk about. We have to be careful about. Also, the angle of incidence is very important as well. Previously, in the example we talked about, we only talked about normal incidence. Light was just coming in straight down, right, into the interface. In reality, of course, that's not the case. You have all kinds of angles, right? The sun is moving across the sky. So it turns out the angle of incidence is, of course, important. At small angles of incidence, you might get a small amount of reflected light. Most of the light can go in. However, at large angles of incidence, even with a good anti-reflection coating, you can get a large amount of reflected light. This is a very hard problem to solve. People are still working on approaches to solve it. And this is an example curve that shows reflectance versus angle of incidence. where as the angle increases, of course, the reflectance increases. So you're losing more and more light. Okay. Difficult problem to solve, by the way, which is, by the way, another reason why you track the sun, right? Track the solar panel, right? So in other words, if you have a sun, solar panel straight down, that's perfect, right? This is the ideal situation. However, during the morning or in the evening, the sun is out here, the light's coming in that direction. You really want to tilt the solar panel. And that's called tracking the sun, as we all know, right? And the reason to do this is exactly because of this loss right here. So now you kind of know. Okay. Okay, so oops. Let's take a look at a few examples. What is the, and I want you to try to do it, have the answer here, but I want you to spend about 30 seconds. I'll give you 30 to a minute or so to answer this question after I explain it. And feel free to discuss with your teammates or your neighbors. It's not related to your project. So the question is, what is the thickness of an anti-reflection coating of silicon nitride, which, by the way, is a very common material that's used for anti-reflection coatings and is very cheap material, to reduce reflections from a silicon surface, which is a proxy for a solar cell, at normal incidence, so at 0 degrees. And then the trick question is, what happens at 45 degrees incidence? Okay, let's do the normal incidence first. Silicon nitride, I'm going to give you some hints. Let's assume the refractive index of silicon is 3.5. Index of silicon dioxide, I'm going to say, is roughly 2.25. And not exactly right. We'll see the actual numbers later. So I'll let you think about this for about a minute or so. How would you answer this question? What is this thickness based on what you know so far? Feel free to discuss, obviously. Any suggestions so far? I couldn't hear it, but okay. Well, in the interest of time, I'm going to move on. So, of course, how do you solve this? It's we worked this out before, right? Normal incidence is shown here. We want to make sure that 2 times d is the distance. Sorry, was there a question?
No.
Okay. Because it bounces off like that. And this is the refractive index of the nitride. You want that to be equal to lambda over 2. It's exactly the same problem, right? So you plug in the numbers in the, and I'm not going to plug in the numbers, but you can solve that. And then D just becomes lambda over 4 times n prime, right? Now, oblique incidence is a bit more interesting because you have a situation as shown here. Part of the light bounces off there, part of the light bounces off here. So the difference is now this distance, right? This is the optical path length. So now you have this cos theta or cos q term in the denominator. So then D just becomes lambda over 4 n prime, but now multiplied by cos theta or cos q. Right? So you can see that you are going to thinner and thinner distances. Now, one very important observation I want you to appreciate here is that this and this are different. So in other words, if I design an anti-reflection coating for normal incidence, that will not work well for oblique incidence, or may not, depending upon how oblique it is. And corollary is that if I design a good anti-reflection coating for oblique incidence, it may not work for normal incidence, right? It's a really difficult problem to make an anti-reflection coating that'll work for both angles, small angles as well as large angles. And of course, people are clever, so people have figured out ways to solve it. And let's talk about that next. This is the idea of index matching. Okay. Now, as I said at the very beginning, the main reason we are having this reflected losses is because there is an index mismatch between air, refractive index of 1, and the solar cell, silicon, right? This N is, like I said before, about 3.5 or so, which is quite high, much higher than N1, right? And that's the reason you're getting this loss. And we'll talk about Fresnel losses, quantify that later. Now, if you could come up with a way to minimize that transition from 1 to N, then you can avoid the losses. So in other words, if I could design something here, there the index varies from 1 all the way to N in a smooth fashion. Like if I plot the refractive index versus thickness, and I have a very smooth variation like this, then I can essentially get rid of all the reflection losses. And in fact, I can do this. If I can do this for all the angles, then I can get that this reflection minimized for all angles as well. And this is also referred to as incoherent effect because you're not trying to take advantage of interference. This is really looking at all wavelengths and all angles simultaneously. Now, it turns out this is a very difficult problem. So, I mean, if we had more time, I'll ask you to think about brainstorm ways to achieve this. But I'm going to move on. But something you can do as a homework, optional homework, of course. But and there are many ways to do this, by the way. One obvious approach is exactly as I've drawn here. I have a slightly smaller index, right? So let's say this is 0.9 and this is 0.8 n, and so on and so forth, 0.1 n, and then eventually 1, right? If I can put in different layers of different materials with lower and lower index and achieve this, I can do this. However, it turns out that getting very low index close to 1 is really challenging, right? Only air or vacuum has index of 1. Getting such very low indices is really difficult to do with actual materials. There are some materials, special materials like aerogels and so on that can actually achieve this, but it's really challenging. So it turns out to be a difficult problem. A very clever way people solve this problem, and I'll show you some examples of it, is to make really, if I were to think about this, really small pillars, which are pyramid shape or conical like that. Now let's think about why this works. Okay. Now, if I start at the very bottom here, and this is really small, okay, think about this distance as being much smaller than the wavelength of light. So if I were light and I'm traveling from top to bottom, at the bottom, of course, I see the full index N. But as I start entering this pillar region, what happens? I start seeing a little bit of air here, right? That means my index is now slightly less than N. Then I keep going up, it's more or less than N. And so on and so forth. Until I reach here, it's mostly air, so it's really close to 1. And once I'm up here, of course, it's equal to 1. So this is a way to accomplish the effect that I'm drawing here. Very clever way to accomplish it. Of course, this material itself is silicon. I'm just changing the geometry of it. Now, people spend many years trying to develop a cost-effective manufacturing approach to do this. And nowadays, they actually have commercial products, and I'll show you one example of this. This is work in the last few years or so from, I believe this was a group at either Idaho National Labs or PNNLs, Pacific Northwest National Labs. The technique was, by the way, invented by professor at Harvard, actually. So that you can see the structure here where they made these pillars that I just, or conical shapes that I talked about. So it's like a grass, basically, right? Now, you can see the this is microscopic, right? This is really small. Looking up here, you can see the effect. So this is the silicon wafer with no no grass. I'm going to call this grass. And this is with grass. So clearly this acts like a mirror, whereas this, it acts like a black hole, like all the light is absorbed. So it's fantastic. This is a great solar cell. This is a very poor solar cell. Of course, none of these are solar cells. This is just showing the effect of the reflection. And if you're interested, there's a link on the website to read through. So this, they call this black silicon, and there's actually an important company called Psionics that was spun out of this. They make not only solar cells, but also photo detectors and things like that as well. And night vision systems for military and things like that. So there's some details of that. And some more examples. So here, instead of the grass, they have these pillar-like structures more regularly ordered. And by changing the shape and the location of these pillars, essentially the geometric configuration, you can actually get really, really reflective or non-reflective structures. So lots of really clever innovation happening in this space, which takes into account optics, photonics, but also manufacturing techniques and large-scale manufacturing, because of course for solar cells and other applications like glasses and so on, you need very, very large areas, right? So it needs to be cheap. Now, excuse me. Now let's spend a little bit of time thinking about the very, very simple theory. So let's take a very simple, and we're going to do this with a simple example. Let's take the example shown here, which is, by the way, this is an example that you will go into a bit more detail in about 2 weeks on the lecture on light trapping. So I'm not going to go into much detail of that, but I want you to think about this problem that we're going to solve when you actually hear that lecture, and I will remind you. Now, what is this problem? Okay. I have a silicon solar cell. So this is my solar cell. I want to do something to it. In this case, I am texturing it, shown there. Okay, I'm texturing it. I'm making some roughness on it. And then I'm coating it with something called PMMA. This is polymethyl methacrylate, but all of you know this as simply plexiglass. This is simply plexiglass, very cheap plastic. And then we have air. Now, it turns out if you do this, you can actually create a very cheap, simple, effective anti-reflection coating. So let's try to calculate and see why it works, okay? First of all, notice the refractive indices here. It's useful to know that the refractive index of plexiglass is in between the refractive index of silicon and air. So that's an ideal material. So that's why we chose that material. First, it's cheap. Second, and it's easy to process. Second, it has the right index. So that was good. Now let's try to do the analysis. So we have to define some parameters here. First of all, we define T incident, which is the transmission efficiency from air to PMMA. So if I start with 100% of light here, I end up with T incident percent of light inside here. So it simply says how much light is lost up here. Okay, that's easy. Eta. Eta is the absorption factor of the rear surface of the PMMA, including transmission to silicon. So eta is simply saying how much of the power essentially ends up going into the silicon, which is good. You want that to be as high as possible because you want trying to absorb that light, right? So corollary, of course, is that if I have 100%, and I'm gonna write this in. Let me erase this. I'm going to write this in fractions instead of percentages. So let's get rid of this. Easier to think about. So let's say I have 1 coming in. I have T incident, which is less than 1 going inside. Okay. And what comes in here is eta times T incident, right? Because T incident is what's incident here. And what's going in is that. And what's reflected then, of course, this is T incident minus eta times T incident, right? Everything else is reflected because there's no absorption. So I can simplify that as T incident times 1 minus eta, which is what's shown here. Okay, so that's the reflected light reflected back into this PMMA film. Okay, now let's keep going to see what's happening to light. We can calculate the absorption at each reflection event and add these up. Okay, now let's try to do that. So again, I'm going to redo this. I get 100% or 1 light coming in, T incident inside, because I've lost a little bit of light out here. And as we just talked about, I get 1 minus eta times T incident here, right? We just talked about it because eta times T incident went in here and got absorbed by the solar cell, which is good. And here I will have another reflection event whose which has a escape probability defined at the critical angle now. Okay, now it's the critical angle. So if you remember, we talked about this before. We have a critical angle. How much light is reflected back is given by this expression. If you remember, this actually comes from Snell's law, where T bar escape is just a normalization term. Let's not worry about this for the time being. I'll come back to this point later on. But really, it depends on 1 minus 1 over 2n squared times T bar escape. Now, this n is the refractive index of the PMMA that we're talking about. So this represents the total internal reflection that should ideally happen here. Okay. Then I have a second absorption event. So here I have what's coming in here. I'm going to rewrite this as 1 minus, sorry, let me write this properly. What I have here is 1 minus eta times T incident times 1 minus T escape. I'm going to put a bar. The bar has to do with angular averaging. Not so important for now. 1 over 2n squared. Okay. Now that's coming in. And what comes out, all I have to do is multiply it by 1 minus eta again, right? Exactly as here. I multiplied by the 1 minus eta to the incident light. And in this case, this is the incident light, and I'm going to multiply by that term. Same thing. And I keep going. It's an infinite series, right? Keeps going forever. But of course, the numbers get smaller and smaller, as you can imagine, right? Because you're absorbing, every time you absorb, you're losing light, right? So less light is reflected. But this is a very simple geometric series, which you all know how to solve from high school math, right? I can write the pth absorption event by this term, where I have this power p. And these, remember, these things are less than 1. So every time you raise it to a power, it's a very small number. At some point, these numbers go asymptotically to 0. And I can write down the total absorption in the solar cell or the silicon to be the sum of all the absorption terms. Okay, so I'm simply adding up the first term. And I'm actually taking out a common term here, but I have the first term here, second term here, third term here, and so on and so forth. Of course, there's a simple geometric series and a very simple expression to solve it, right? And you all know how to do that. So simple algebra. A couple of interesting things, of course. Again, our goal here, our design goal is to maximize absorption. So of course, how do we maximize this? You want to make sure that the transmission into, this is the T incident, into the PMMA is high as possible. The absorption at each event when it hits the PMMA silicon interface is also high. And the rest of the stuff is straightforward. You want to make sure this N is as high as possible, but you don't have much control over it. It's just a choice of material, right? N you can't really control easily anyway. And you also want to make sure that this T bar escape is as small as possible. So you lose as little light as possible from the top interface. Again, you don't have a lot of control over that at this point anyway. There are ways to do it. So really, you really think about eta and T incident. Now, the T incident is important because that depends on the refractive index of the material. So let's plug in some real numbers instead of the algebra. So refractive index of PMMA is 1.5, silicon is 3.5. Plug in eta. Eta is the Fresnel loss, is this term. So 1 minus the Fresnel loss is assumed to be the absorption because we are assuming everything else is absorbed. It's an assumption, but it's a reasonable assumption. You plug it in. The Fresnel loss is defined by the difference in the refractive indices squared. So you get this number and you get something like 84%. Now, T incident also you can compute also as a different Fresnel loss, but with respect to PMMA and air. And you get something like 96%, or you lose about 4% of the light. Put it all together, we're going to make this assumption, T bar escape is T incident. This, by the way, I'll come back to at the very end. It's based on a paper. Then the absorption can be easily calculated by the equation that we derived, and we say, okay, 92% of light is absorbed. Now, this is very, very important. What we're saying is that by roughening the surface of the silicon, let me go back to the geometry so we all appreciate what we're talking about here. Oops. By simply roughening the surface of the silicon solar cell and by adding a PMMA coating on top, these are very cheap things to do, I can get 92% of the light absorbed. That's a big deal, because if I do nothing, I'll only get about 70% of the light absorbed. And that's bad, right? You want to get as much as possible. So that's the reason why this idea and this approach of analysis, this is of course a back of the envelope calculation, but hopefully gives you some intuition. So let's summarize this concept. 90% of the light gets absorbed in silicon and the PMMA silicon interface. So about 10% of the light is reflected back. So PMMA on top of randomly textured silicon acts as a decent anti-reflection coating. Now, if there is no PMMA or texturing was present, remember in the picture you saw before, the silicon wafer is simply like a mirror. So the reflectivity is 31%. So as I said before, about 69% of the light makes it. This is not good, right? You don't want to lose that much energy just because you did not do something simple and cheap, as shown here. And I would say 100% of the solar panels you buy today actually use a bit more sophisticated techniques than what we're talking about here, but they do have an anti-reflection coating. Now, you can also think about the index matching idea without the texturing. If I take a silicon that's completely polished like a mirror, and I can add an anti-reflection coating on top of it also, if I want to avoid the texturing. Sometimes you want to avoid it, which you will, by the way, touch on when we talk about the review of solar cells in the next Tuesday's lecture. Sometimes those texturing can cause defects in the silicon crystal structure that can affect the efficiency of the solar cells. So sometimes you want to avoid that. In that case, you want to use a smooth ARC. In this case, all you can do is try to match the refractive index between these two, try to mediate the index variation between those two. And there are many ways to do this. An example that you saw before, you can take an arithmetic mean and you get something like 2.25, which is serendipitously, this turns out to be the index of silicon nitride. So that's what a lot of people use actually. And if you try to compute what the reflection losses are, you have two interfaces, right? You have the interface on top. So again, you have the air, you have the special material, and then, whoops, and then you have silicon. Now you have a loss up here and you have a loss up here. So loss up here is this, about 15%. And the loss up here, down here is that, about 7.4%. You add them up and you get about 22% loss. So it doesn't do as good as the texturing, but you can do a little bit better than not doing anything at all. So again, these are all, I mean, of course, in an actual device, these are a little bit better. So just to conclude this whole part of the lecture, the PMMA plus texturing proves to be a very effective anti-reflection coating due to the effective light trapping. So remember all those bounces that happen? This is referred to as light trapping. And you will talk more about this in about 2 weeks. So the total reflectivity can be reduced to about 10%. Note that all solar cells are encapsulated in glass for protection. This happens all the time, right? Because you got to protect it from the weather and so on. So there is always a reflectivity of 4% off the top, then 1.5. So reducing this to about 11% or 10% is pretty good, since 4% is the best one can hope to achieve. So it's pretty close to the theoretical limits already. That's all we're trying to say here. And that's the last slide I want to talk about in anti-reflection coating. And before we move on, I just want to, I'll give you a short break, but I want to, let me show an important thing here. I'm going to go back to the website here. There is a paper that I linked here. If you click on it, sorry, it's an important paper. We'll actually revisit this in 2 weeks, called Statistical Ray Optics. The second part, this paper, we'll go through this paper later. The second part of this paper talks about the anti-reflection coatings, and that covers the math in a little bit more detail than what I talked about, but it's essentially what's covered in this paper. And we'll talk more about this later on. And the person who wrote that paper, by the way, is a very famous guy, Eli Yablonowitz, who's now a professor at Berkeley, but he's famous for inventing the photonic crystal and has been nominated for the Nobel Prize as well. In any case, now I want to move on to the next topic. But let me stop here and see if there are any questions before we jump into it.
Any question? No.
Okay, good. My advice, by the way, is to just take a quick look at the paper I just showed you and just make sure you're aware of these things because, again, I know we don't have a problem set or an exam related to these topics, so but don't ignore it because it's important that you understand some of these simple problems, right? Hopefully what I'm trying to do is to see you, have you think about actual real world problems and connect it to the theory and basic concept that we learned about during the first part of this class. Okay, now let's move on to the second topic for today, which is related to the measurements of photovoltaics. Now, of course, the solar cells are not the only topic for this class, but they are a very important area for us. So it's important to understand how we characterize them, and how we characterize them is important in the industry. Now, first of all, theoretically, what are the key parameters to measure in a solar cell? We have current and voltage, right? It's an electrical device. Light gets in. So again, what is a solar cell? Very simply, you have light coming in, photons come in, H nu, and current comes out, electrons come out. And we know power is current multiplied by voltage, right? So current and voltage needs to be measured in order to compute the power. So there's some intensity here, which is watts per meter squared. I have to multiply it by the area of the solar cell to get the watts. And then I convert it to current, I still have watts. So that's some efficiency. So the watts out divided by the watts in gives me the efficiency. So these are very important things to think about, right? Okay, whoops. So what, because the solar cell is a reverse bias PN junction, which we'll talk about more on Tuesday, its current voltage characteristics looks like as shown here, where if you plot the voltage represented by U and the current represented by I, typically, by the way, we also do current density, not just current. And the reason is you normalize the current amperes per meter squared to the area of the solar cell. So something to keep in mind. But in any case, because the reverse bias device, as the voltage increases, the current is negative. It's a reverse bias. So the current is negative. It's flowing in the opposite direction to the voltage. But as the voltage increases, the current increases. And because you're getting this minority carrier injection that's happening. And then we'll talk about that on Tuesday. And the current increases until the voltage, the current actually becomes zero. So current is zero means it's open circuit. So this is referred to as the open circuit voltage. That's what the OC stands for. And after that, it becomes forward bias. You have majority carrier injection, and you get current essentially exponentially increasing. And the place that you want to be for maximum power generation is this point here. It turns out because that is where the product of I and U is maximum. And of course, the product of I and U is the power, right? So that's why that is an important case. So let's plot this data a little bit differently in terms of power. So that's what's shown here. So again, we have voltage. So now it's in V, sorry. And we have current in this axis or power. So the red curve is the same curve that we saw before, except that it's flipped up. So ignore it. So it's actually plotting the absolute value of the current. Okay. But the important curve here is the power curve, which is shown in blue here. This is the product of current multiplied by the voltage. So of course, as voltage increases, this increases linearly, but it reaches a maximum point, after which, because the current is decreasing, the power also decreases. Eventually it goes to open circuit because the current is zero here, right? So the power is also zero. So that's not, you don't want to be there. This is called short circuit current, SC, short circuit. Short circuit, why? Because the voltage is zero. And this is called open circuit. Why? Because the current is zero. There's no circuit. So it's open. Now, there's a couple of important terms to aware of. So first of all, efficiency is simply the maximum output power. So this point here divided by the input power, which is of course the light, right? This is the intensity of the light multiplied by the area of the solar cell. That's efficiency. By the way, that's a really difficult thing to measure accurately. We'll talk more about that shortly. Now, there's another term here called FF, and it stands for fill factor. And this is simply the ratio of the maximum power that you can get out of the solar cell divided by the product of open circuit voltage and short circuit current. This multiplied by that, which is simply the area of this rectangle, right? This big rectangle. So all it's saying is the maximum power. How close is this to this ideal situation? So more square the IV curve is, the better the fill factor is, and larger fill factor is always better. And of course, fill factor is always less than 1. So as close to 1 as possible is what you'd like to get. Okay, so these are the important parameters. Now, how do we measure them? Of course, we have to do electrical measurements, but in order to do electrical measurements, you have to illuminate it with something. And then we talked about this before. You need to have some standardized illumination setup. And for terrestrial applications, you have systems that have 1,000 watts per meter square, approximately, and referred with a spectrum that's the ASTM global spectrum that we have seen before, and there's a temperature condition. So these are standardized measurement conditions. Now, if you do concentration, then of course the intensity goes up. The other things are the same. Actually, sorry, this is the direct, so it's not the same. And it is direct because we know that global includes diffuse light as well, and diffuse light cannot be concentrated. So that's why it's direct. We saw this before. And of course, in space, the intensity is different because the absorption in the atmosphere does not happen. This is AM0 we talked about. And the temperature can be different. In fact, this is a little high, in my opinion. And I think in actual space operation, this is much lower. So in any case, those are standard numbers. And there are a few other things, parameters here, which, again, you should be aware that these things exist. You don't need to memorize any of these, of course. Now, the area definition for efficiency measurements is very important. For non-concentrator cells, the entire cell area is used, including area covered by cell grids and contacts. So when we look at a solar cell, there's always these grids that you see running across the solar cell or solar panel, and these are the wires that carry the current, right? And they of course shadow the light, so they actually contribute to efficiency loss, but in actual measurement you actually do need to account for them. So you take that into account when you do the measurements. Now, for concentrator cells, the illuminated aperture is used. Now, what does concentrator cells mean? That means you have a concentrator, like a CPC, right? And then you have a solar cell. So in the case of the CPC, this area is used, area of the concentrator, whereas this small a is area of the solar cell. But this is the area that's used to compute the incident power. Because if you keep in mind, the input power is simply the area multiplied by the insolation of the sun. Okay, so that this choice of this area is important. Of course, you have to use this area because that's what you're collecting the light over. So you have to be careful how these things are measured. Now, calibration is very, very important. So in my lab, when we used to do solar cell efficiency measurements, we used to have to purchase a calibration sample whose power is very, very carefully measured by NIST, by some standards authority. So in this case, you have an incident power Pin. It has to be calibrated very carefully. This is done using a reference cell, which is carefully constructed, such that short circuit current has been calibrated with respect to a known reference spectrum, one of the standard spectra that we talked about before. Of course, the air mass is important. We talked about this briefly before. Depends whether you're measuring with an air mass 1, which means that the light is directly overhead, or air mass 1.5, which is the standard use, where it's like about 46.19 degrees, roughly halfway in between. And I won't talk much more about this, but that's something you should be aware of. The choice of the illumination spectrum is also quite important, because you don't typically have a source that can perfectly mimic the standard spectrum. So in this case, you have to correct for the variations in the spectrum. And the way you do it is not terribly complicated. What you do is this is what you're trying to get. You're trying to get the short circuit current of a test cell under a reference spectrum. But what you can actually measure is with the source you have, which is a test cell under a source spectrum. It's your source that you have handy. What you have to do is scale it by this factor here, which the numerator is the reference cell under the reference spectrum, which is the short circuit current density, current of the reference cell under reference spectrum, which is something you are provided by the manufacturer of the reference cell, or you can measure it yourself, because it's provided by the manufacturer of the reference cell, because you don't have a reference spectrum. But you can measure the reference cell under your source spectrum, that's your source, and you compensate for it. So it's simple scaling. This factor of M is simply the difference in the spectral mismatch factor, which is basically saying what is the difference in spectrum between the reference spectrum and your source spectrum. Again, the pretty simple scaling factors here. So it's just pointing out that the illumination spectrum is actually very important on what you use when you do these measurements. Also, you should be aware of current voltage artifacts like hysteresis. Those of you who are in EE are probably very familiar with this point, and those of you who are in mechanical engineering, of course, also are familiar with the hysteresis in motion as well, right? Stages and so on. Exactly the same thing happened. All it's saying is that when you do these current voltage measurements, if you go in one direction, you measure a curve which looks like that, and when you do in the opposite direction, you get a slightly different curve. This is called hysteresis. Of course, this is bad, because then you're not getting a good reading from your device. By the way, the physics of hysteresis is very complicated, and I won't go into any detail, but it turns out that you can solve this problem by doing a very, very slow change of voltage or steady state measurements. So something to be also be very careful about. And the current voltage curves, of course, change with exposure to light. It's a nonlinear curve. So this IV curve that we plotted here depends on the intensity of light. And I won't go into much detail, so you have to be careful about how this is done. And in the case of SIG cells, this popular low-cost cadmium sulfide copper indium diselenide cell, these are commercially available, inexpensive thin film cells. You have to do something called light soaking to avoid this issue. And what you do is you take the solar panel after it's manufactured and put it under a light source for a certain amount of time. It kind of looks like that. In fact, I toured one of these factories a couple of years ago, and this is indeed exactly what they do. And then after they do this light soaking for many hours, they can do the measurements, and it's very, very stable. Of course, you also have to be worried about contacts resistance when you do these measurements. Of course, you have to solder the contacts, so there's some contact resistance there. So you avoid, and these are the bond pads, some of you are familiar with, also has contact resistance. So to avoid these things, you have to do something called 4-probe measurements. A little bit outside the scope of our discussion here, but something you should be aware that it needs to be done in the case of very precise measurements. Okay, The last topic I want to cover is on a little bit on optical instrumentation. Now, the reason I want to talk about this because there